do have some other plans from the extension of that paper, which is the method of factorization. Okay, when you have two big numbers and you multiply those, you will have a huge number. But if you were to factorize that huge number into to find two other number, you will have a list of probabilities of numbers that you can multiply. So he did manage to resolve those issues, and it triggered a hustle within the realm, because when you have a tool or you have a way to do factorization, it means that the encryption that governs the transaction, the security transaction of banks, or even encryption of the network, is based on RSA. It's based on AES, which goes back to the factorization issue. So if you can have a tool or have an algorithm to crack it, then it means that you have the ability, the security of the whole nation regarding whether it's finance or government can be cracked. So that is why he was questioned by NSA and the defense because of his algorithm, because of his finding. So when that happens, when that occurred, actually it's just a algorithm, and it can only happen if today we can have 100 qubits fault-tolerant quantum computer. Then sure, algorithm can work on that condition, and we might have a problem with our security. But again, people do try to use those algorithms in an actual quantum computer. That is when, in 2001, moving towards 2005, people tried to create a working quantum computer with at least a couple of qubits. Okay, and in 2017, it was announced that IBM and several others managed to create 53 qubits. Actually, it's quite huge when you have 53 qubits. Just imagine your normal computer that do have a 16 gigabit RAM, okay, can perform a calculation, a simulation of 4 qubits. But when you add another qubit, the numbers of RAM that is required will double just by adding one more qubits. So having 53 is quite a huge achievement. And the biggest talk was in 2019, where Google announced they have achieved quantum supremacy. This I will explain later. But having said that, after Google announced in 2019, China announced that they have achieved quantum supremacy using a photonic-based quantum computer. So from there on, people will try to increase the numbers of qubits, but that number of qubits is actually there are issues, because when you have numbers of qubits, it doesn't mean that all the qubits can work properly. That's the problem that we do have in quantum computer. But it doesn't stop people to plan ahead what are the event that might occur because of this development in quantum computer. So that's why we in the trend we will see people talking about the posts of having question the quality of cryptography. That's why the idea of post-quantum cryptography arise. And then when researchers explain about quantum supremacy, quantum advantage, it's just based on theoretical method on simulation mode. But it is believed that in 2023 and above, we might see a working concept of quantum advantage in the real world. Okay, and by that, there is a lot of discussion within the finance where quantum computer works very well to find optimization um, uh, in profilings, in risk analysis, okay, in data that are huge. Okay, and then moving forward, there are also researchers that are working in quantum machine learning. It's either using machine learning to solve quantum problems or to speed up machine learning using quantum mechanics. Okay, so let's talk about the hype that Google announced back then in 2019. Okay, so when Google announced it, it was quite a huge thing because Google was examining the function of their processor. They call it Sycamore, and that processor is a 52 qubits, and it can perform a calculation within less than 200 seconds that takes a classical computer 1,000 years. And that is where the term quantum supremacy rise. But again, IBM announced that they can perform the same calculation using their quantum computer, using their super computer within 2.5 days, as compared to Google's claim 1,000 years. So that was an issue back then because it's either Google were explaining were prematurely proclaiming they achieve quantum supremacy, or might be IBM was too jealous that they are not the one. So the discussion, what we can come up on those kind of conditions are two things. One is the term of quantum supremacy and quantum advantage. And another thing is the practicality of quantum computer. Because when Google announced that they achieve quantum supremacy, it doesn't mean a lot in the real world application. Okay, quantum computer does not cannot and will not replace the classical computer that we have today. But it can perform some tasks that cannot be performed by classical computer. For example, um, if anyone remembers about Yellow Pages, okay, if a person were asked to search for a number, given that they receive a name, for example, Ahmad, okay, so they will go through the index of Yellow Page, and then they will find the name. They start with the alphabetical order, A, Ahmad, and then the address, and then they will point it to a number. So that's how it works. But if you were given a phone number and to search for the name of the owner of that phone number, it will be quite hard for you to use the indexes in Yellow Pages, isn't it? But in quantum computer, that's not a problem. We have Grover algorithm that can solve that. It's like having a test. If I were to put an analogy for quantum computer, it's like having a Tesla car with those roller coaster mode, okay, in steroid. You just turn it on and we just launch. So those kind of cars for normal usage are useless. You cannot use a car that when you turn on, it's on that roller coaster mode. You will keep on hitting everything. But when you put that Tesla car at a direction and turn it on, and you want to move to that direction, it will move at the fastest ever manner any car cannot compete. So that's the analogy of quantum computing. It doesn't solve normal problems, but it will solve a problem that no classical computer can perform. So the terms of quantum advantage and quantum supremacy actually intertwine each other. But basically, to understand it, it's better to understand by the term when you have quantum advantage, it means that the quantum computer can perform a task that can perform a task better than a classical computer. That's quantum advantage. But if you say that you have a quantum supremacy, you achieve quantum supremacy, it means that your quantum computer is performing a task that no other classical computer can perform. So that's why when Google announced that they achieved quantum supremacy, that's a huge thing actually. So is that quite true? I mean, is quantum computer is a hype? If we look at the numbers of investment from 2012 until 2018, we will see that in 2012, there's an investment of a single company that received $46 million, and that company is D-Wave. They are the one that produced the first working quantum computer to Google, to Boeing, to Airbus, all those big names. And then the numbers keep on increasing. And if you notice that in 2017 and 2018, the numbers of investment total up is 451 million, 4 times compared to the previous 2 years, which is in 2015 and 2016. It does not stop there. If you look at the locality of investment, most of the investment are in North America, in Europe, in the UK, in Australia, in China, and the numbers of patents also increase. Since 2012 until 2018, we see numbers of patents related to quantum key distribution, related to quantum computing and other quantum technologies. Starting off with China, where the amount of patents for QKD was quite enormous. Okay, followed by US, Japan, Canada, South Korea, and United Kingdom. Okay, this is the landscape of all the companies that are related within the supply chain of quantum computer. As of today, there are 258 companies, okay, and it covers from the segment of hardware and components, cryogenic system, okay, the lasers and light source and other components to construct a quantum computer, okay, those suppliers. And for your information, if I'm not mistaken, a researcher in UTM did mention, Dr. Tan, he's working on a quantum computer, but in Singapore, he said that if you were to purchase a cryogenic system, it will cost you at least $2 million. Okay, that's just the price of the refrigerator of the system. And to transport that, there's another cost for transportation, there's another cost for installation, and there's another cost for setup to configure. So it's quite a highly budget kind of activity. Okay, so moving towards quantum processing unit, okay, they are most famous superconducting, where the players are D-Wave, IBM-Q, AWS, Google AI Quantum, and also other companies such as Rigetti, Kilimanjaro. These are the famous quantum processing units that's available. But it doesn't stop there, because there are others also, such as ion trap techniques, atom techniques, photonics techniques, and silicon techniques. Okay, the famous names are such as in ion traps, IonQ, and Quantinum, a spin-off from Cambridge or Oxford, if I'm not mistaken. And in photonics, it's Xanadu and PsiQuantum. Okay, those are the huge names in quantum computer. So previously, prior to 2009, you don't see much of this. But after 2009, the numbers of startups, the numbers of companies related to quantum computer just skyrocketed, and investment are keep pouring into it. Okay, because it's not just about the hardware; it's also about the software. So companies such as Zapata, Multiverse, Riverlane, those are companies that produce the OS, the software, the back-end systems, the logic systems for the quantum computer to work. And if we look at the numbers of also the company that produce simulations and also cloud, bigger names are in there, such as NVIDIA, Huawei, Azure, Google Cloud, and AWS. And some of these companies do provide access to their quantum computer and also others quantum computer. Okay. And if you look at the application side of it, there are users from material science, finance, life science, and others also. Okay, the numbers of financial institute that do want to have quantum prototype in their division keeps on increasing from 2020 to 2021 and 2022. Okay, now knowing that we know that quantum is here to stay. Quantum computing is not something that people say that is far to reach, because we have 258 companies and we have a quite number of end users. There are prominent names that do tests, that do prototypes and pilot projects related to quantum computer. So how does the quantum computer works? Okay, before I move towards how quantum computer works, I need to explain the difference between quantum computer and classical computer. In classical computer, it's about calculating the changes of transistor of either 1 and 0. But in quantum, we do not call it bits, we call it qubits. And qubits is, if I were to put in analogy, it's like you have a coin and then you spin the coin. So the state of 1 and 0, you can have both state at the same time by spinning the coin. You can have either 1 or 0 or values in between 1 and 0. Okay, and the numbers of the power increase, if we look at classical, it governs by Moore's law. So the number of increase of power in processing is actually goes linear, but in quantum computer it's not that way. It will be exponential. So every increased number of qubits, it means that the amount of power of calculation or power of computation will exponentially increase. Okay. So in quantum computer, we have higher error rates compared to classical computer. The error rates can be resolved through calculation, through algorithms, because the numbers are quite small. But in quantum computer, it's quite huge. Even the changes of even the heat, the external wave can change the quantum state. That is why if we have a superconducting computer, it has to be running in a cosmic temperature, which is millikelvin or minus millikelvin, something like that. So that's the temperature processing condition. Okay. Now, when I mention about quantum classical computer, it's about having bits that are independent to each other. So you can have one bit that does not correlate with the bits aside. And you can have one state at a time. But in quantum computer, it does not work that way. Quantum computer is governed by three quantum mechanics properties: superposition, entanglement, and interference. Okay, and in qubits, it's either a spinning arrow to 0 or a spinning arrow to 1. Okay, I have to use the terminology of spinning arrow because when we perform, we visualize qubits, this picture over here is actually what we call block sphere. So this block sphere is the method of visualizing the state of that qubit. So it can be 1, 0, or in between 1 in a spinning mode. Okay. Okay, that's the first the first property is the superposition. So when you measure state of a qubit, actually you can measure both. It's either 1 and 0, but in terms of probability. So if you were to have a state of 0, it means that you might have a higher probability. That works. Sorry for the video. Okay. 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 If you have a measurement of 0, it means that you have a higher probability of 0 compared to 1, and vice versa. If you have a measurement of 1, it's actually the probability of 1 is higher compared to 0. And you can have a state where the probability is at the center, where 50% is 0 and 50% 1. That can happen also. So this kind of property is quite it's not common in classical actually. Okay, and there's another property which is the entanglement. So in classical, when we talk about 1 and 0, the state of that bit does not have a correlation with the other bits. But in quantum, it has to be in such manner. Okay, so this is what we call entanglement. The entanglement creates a condition where the measurement, I'm sorry for the interruption. Okay. Okay. Uh, when you have an entangled state of qubits, it means that it has correlation between those two qubits. It cannot work independently. For example, if we have a state, okay, if we have a state where the qubits are okay, sorry again. Okay, just stop here. Okay, if the qubits are, for example, one qubit is in a state of 60%, 40%, another is 15%, 81, 85%, it doesn't work that way. When you have entanglement, it works as a unit, both. So what the outcome is actually a probability distribution of those states, meaning that if anything happen with one of the states, okay, it will affect the whole probability distribution. It's not just one, but the whole. So if you have numbers of qubits, for example, 2 qubits, you have 4 states, and it goes on. So meaning that if you have n qubits, you will have a probability distribution of that n quantum state, all working together in the entanglement mode. So these are the properties that totally is quite alienated for classical computer, but it works fine in quantum. Okay, and the another part, which is the interference. Because when we have that probability distribution, the way how we measure it has to be performed using interference. Okay. So just now when I talk about block sphere, that was just a visualization of it. The actual representation of quantum measurement is in a quantum wave function. So when you have several qubits, for example 3, you are actually measuring the overall wave function of those 3 qubits. So this is where the interference comes in. So it's like a ripple of water. When you have 2 waves constructively interfere, then you will have a constructive interference. Okay, and vice versa for destructive. So when we have the probability distribution, actually those probability distribution, we can only measure one thing at one time. Okay, and how we get that is by increasing the correct answer by constructively interfere it and removing the wrong answer by decreasing it using destructive interference. So you can only have one answer at a time. So hopefully that will be the end of the theory part, and I would explain further for the theory parts. Okay, and this is actually the types of quantum computer that we have currently. We have the atom-based, the electron-based, and the photonic-based. But the most discussed are superconducting, ion trap, and also photonics. So every method, each and every qubit type, there are the pro and cons. For example, superconducting method will have a very good advantage because we are leveraging from the standard lithography process. So that's why the numbers of superconducting, the numbers of qubit in superconducting can increase exponentially from year to year. Okay, but the disadvantage is you have to have that cosmic temperature. So it cannot open in normal. You have to put it in sub-zero condition and measure at that particular time. Okay, for ion trap, it might not. It's more advantage in terms of you don't need to. You can work ion trap in a room temperature, so you don't need to purchase that $2 million refrigerator to cool it down. But when you have this ion trap, actually the disadvantage is um, the connectivity between one ion to another ion. You have to control it very well. Okay. Another thing on superconducting, the disadvantage of superconducting is the decoherent time. Okay, it's actually a time, the time where a quantum state can be measured. So if you have a small time for a quantum state, it means that you have to make sure that you can quickly collect that measurement. If not, it will just disperse like that. So the longer you have the coherent time, the better. Such as in ion trap, you have a longer coherent time. But the disadvantage is you have to have a setting where it's very hard to have a higher number of ion traps at one setting. You will require a big setup. Okay. Same in photonics. Photonic, you don't need. It can work in room temperature, but the problem is the noise because of the loss in photon. And the fourth is quantum dots. Quantum dot is actually leveraging from semiconductor, the same as superconducting. You have to have a refrigerator to cool it down to do the measurement, but the time When you have something that requires cooling process, it means that the coherent time is quite short. So that is why the biggest problem in quantum computer is the fault tolerant. Meaning that if you have a quantum computer for example, 2000 qubits, it does not mean that all those 2000 qubits can work at the same time perfectly. No. So there will be a huge numbers of errors. So research, the biggest research activity is on fault tolerance as current. Okay. Now let's look at the application of quantum computer. Okay. When I do mention about the property of quantum computer can perform something that cannot be performed by classical, it means that there are a lot of nature property that can only be performed in quantum computer. For example, in quantum simulation, right? In either a lot been used in chemistry, where you want to synthesize or create new material. For example, new drugs, new fertilizers, new to improve batteries. All those chemical requires physical interaction, meaning that you have to make an experiment physically, and those physical experiment is high in cost, will take longer time to understand what are the nature of the property, the new material, but that can be performed by quantum computer far lesser time and just through calculation, without the needs of having a high budget to perform the labs, the synthesis, all those things. So that's why it's a lot being used in trying to find new materials property, trying to improve solar panels, try to find the best fertilizers for agriculture, to find improvement in battery processes, battery new materials. That's on the quantum simulation part. In optimization, there's a lot of application such as machine learning, traffic to optimize traffics, and also in weather forecasting. And you might be surprised, big companies doing weather forecasting intensively to identify climate change upfront before those things happen, and it's quite beneficial for the nation, for city councils to plan ahead. And there are other application such as quantum machine learning, quantum communication, quantum algorithm, quantum chemistry. Those are the real application that are being used that we use on the computer. Okay. Now the trend in 2020, we have understand that there are real application, but what are those real application mean to the real world? Okay. So for trend, I only highlight the latest trend currently in 2020 only. So the biggest improvement that we see from IBM was it was able to create a condition where it can multiply the number of quantum bits by not just on top of a wafer. Instead of having a wafer having 100 qubits, you can have two wafers stacking each other, and those two wafers is connected via bridge. That's in 2023. It's a roadmap by IBM where it can manage to do a setup to perform a bridge from one panel to another panel. By having this, that is why they are target to achieve 1 million qubits can can be faster than expected, because they can manage this. Because when you have a material in between the sets of qubits, it's actually hard to control the quantum states. So when you can have a bridge that you can maintain that quantum state, both sets of qubits, that's a huge improvement in superconducting. So that's for IBM, because it just announced this in May 2022. Okay. For Google Quantum, okay, Google managed, this news was in July, this month, 22nd July. So they announced that they managed to come up with quantum virtual machine. So instead of you having to access Google quantum computer, which you need to queue for that matter, now you can have a virtual machine replicating the same thing that is running in a Google AI quantum lab. And this, if I'm not mistaken, depends on, there's a package for that. So you have to register to be the participant to test it. So it's not open to public yet, but there's advancement in there. Okay. Xanadu just announced that they have released the first photonic quantum computer in cloud. Okay, this is a big news because in 2019, people were talking about quantum supremacy, achieving quantum advantage, blah, 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 blah. But in 2031, okay, big companies start to give access to the public to access their quantum qubits. Okay, in 2021 also, there are a lot of companies that try to push their solution to the cloud. That's where you can see Amazon collaborate with Rigetti, collaborate with IONIQ, so that other people can access AWS quantum computer. At the same time, they can perform their simulation in other hardware, such as IonQ or Xanadu or others. So it's a quite huge milestone actually. Okay, and this is an example of a quantum computer software where Zapata is collaborating with auto sport industry, okay, to come up with a accelerated race time analytics, meaning that the optimization of a racing car can be performed in real time. The calculation to ensure what are the optimal setting for that car can be performed in real time. And this is being done by Zapata. I think the only quantum computer company that's into auto racing. There's other company in auto also. For example, quantum computing in Volkswagen. Okay, this is an example of Volkswagen announcing that they are performing quantum computing to understand the traffics, to improve the usage of the roads in the city. There are also, last year, Volkswagen announced that they have used quantum computer to optimize the changes setting within Volkswagen factory. Okay, example, in the process of releasing a car, in process of manufacturing a car, there's a process where when a painting is performed, the factory will lock the design or the process line for painting for a particular model. So when they transfer to another model, there will be an optimization process, and those optimization process will take around 2 weeks for them to rearrange it. But using quantum computer, they can perform that optimization within less than 20 seconds. That was the record for Volkswagen last year. Okay, so now we go to Aiterra Quantum. What is Aiterra Quantum's doing currently? So our core activity are two. One is training. We have a custom train where we design the training for universities or for research group that want to upgrade their researchers to be quantum equipped, so that they can perform quantum computer analysis or simulation or even quantum machine learning, and also certified training, meaning that a training focus on getting the participant to go for IBM quantum computing examination. Okay, and at the same time, we are also do have a service in quantum research as a service, where we do exploration and also R&D prototyping. Currently, we are working with geoprecision, using quantum optimization to understand what are the parameters that can be optimized for agriculture. And also, we are doing work with Unimap, utilizing quantum machine learning to identify property within plants in agriculture setting. So that's all for me. Here I leave a link for those who are interested in further discussion. You can scan the link and put your details so that our staff can contact you. Okay. So I open the floor for any question and answer. For questions.
Thanks, Hafiz. I think I just interrupt first. I think we can open for a few questions from the participant. Any questions from the floor?
Assalamualaikum.
Salam.
Salam.
Okay, the Suzu here. I have two questions related to what you explained just now. Thanks again for sharing. My first question is basically what's the real challenge regarding the ground truth on the quantum development in Malaysian environment. And the second one is how the students, like I think majority during the session today is the students to engage and to explore or probably to start up with some ideas on the quantum research or the quantum study.
Oh, okay. Okay, for question number one, okay, the biggest problem in quantum computing is to have a fault tolerant quantum computer, because currently in any quantum computer type, whether it's photonics, whether it's electron-based superconducting or ion trap, there are a lot of error within the measurement. Okay, such as for superconducting, we have error when we perform a quantum algorithm on a quantum computer. We will design a quantum circuit for it, and we will assign each qubit to perform a particular task. But when we run the system within the current quantum computer, there will have a lot of errors. Errors due to machine, errors due to the architecture itself, errors due to external factors, and those are researchers are trying to minimize those errors. That's why the current state of quantum computer is not totally a perfect quantum computer. We are in a stage where we call it near-term quantum computer. So it means that we still can perform simulation, we still can perform calculation, but the numbers of error is valid. So if we want to achieve the application of, for example, Shor algorithm in quantum computer, and it can only be possible if we can have 1,000 qubits, 1,000 working qubit. So for a current state, we need 1 million qubits to ensure that 1,000 qubit works perfectly. So that's why there's a lot of research in there to come up with a fault tolerant quantum computer. And then there's also research in quantum optimization. Okay, but this is more on study based, meaning that the case is there. Example in fertilizer, in chemical discovery, drug discovery, and in weather, because the data are such huge. The parameter are if we were to perform it in a normal NVIDIA machine learning, it would take a longer time. So some of those calculations can be performed or can be optimized using quantum computer. That is why when normal quantum computer perform, it will perform within seconds, because as I mentioned in the slide about how quantum computer works within the interference property, we only measure one thing within the whole probabilistic distribution. So that's where quantum computer achieve quantum speedups. So that's first. Meaning there's a lot of research there. Okay. For the second question, how would a student start? Okay. First of all, a student has to have a good understanding of linear algebra, and also okay, in terms of quantum mechanics, having the knowledge of those three parameter of a quantum computer is more than enough to start off. Okay, but when you start developing your own algorithm, and you start designing your own quantum circuit, okay, that is when more technical knowledge is required. So, and if you are if a student want to start off, I would suggest that you start off with IBM Qiskit first. There's a lot of option. There's Azure Quantum with Q hash. There's Google TensorFlow for quantum. There's also Xanadu for quantum machine learning. If you start from that, it'll be quite hard because it's quite intimidating that there are a lot of things that you don't understand. But from a IBM perspective, there are some tutorials, there are some trainers that do provide basic understanding. Because even some of the stuff in quantum unit in IBM are not physicists. Some of them are from finance and from university way I mean a university that you haven't heard of in Africa, because those people are actually being trained, because in 2019 IBM did launch a program for 16 universities in Africa to expose them for quantum computing, meaning that you don't need to have a quantum computer. You can perform your quantum computer even tengah masak pun. You can do that. So my suggestion is start off with having a good understanding of linear algebra, and then probability distribution. That's important. And also, if you want to touch your toe, then go for Qiskit IBM first. Any tutorial, and there's a lot of book for Qiskit IBM.
Okay, thanks, Hafiz, for answering the first two questions by, I think, from Dr. Zul. Is there any other questions that you want to ask, or even maybe if you want to share your ideas or anything, feel free to do that. To the floor if you have any questions. Okay, we have one, Cik Hafiz, from Ahmad Ghaffar. Thanks, sir, for the information. So, in short, the limitations are the high power consumption, accurate errors. My question is, with this limitation, does quantum computer have application right now?
Yes, definitely.
Mm.
Meaning that a lot of activities is being done in quantum simulation. For example, Volkswagen managed to shorten their optimizing process, and then there's an example of um, weather forecasting. IBM is actually doing it, weather forecasting, using quantum computer and analyzing the weather, because in normal weather forecasting, it's actually a forecast of the next 2 days or the next day. Okay, you cannot have a prediction of the whole month. So using quantum computer, you can do that. You can have a prediction with a certain amount of precision up to a month. Okay, there's also a lot of activities in finance. Okay, using quantum simulation, because quantum simulation can be performed in a setting such as hybrid quantum classical computer, meaning that part of the process of calculation is being done in quantum and another part is being done in a classical computer. There are a lot of that in finance. So, for example, in finance, for risk analysis, credit risk analysis, to identify stocks portfolio, because there's a lot of parameters. If you want to understand which stock will has a good profit margin, okay, data that are huge. You can perform quantum simulation in a setup where there is a hybrid.
Okay, thanks, Cik Hafiz. I think hopefully it answer you, Ahmed Ghaffar. I think they have another one. Okay, my question is about quantum work with frequency domain of spatial domain. I mean, with deep learning, the second question, what is the simulation to do it in quantum? I think the same guy asking the same thing. Okay. I think if summary this way, quantum work in frequency domain.
Yeah. Okay.
Definitely.
There are actually what I list just now are just the four main quantum computing. There are others, and there is a list of it. The reason I didn't highlight is because, for example, topology quantum computer. Topology quantum computer works in a condition where you have a quasi of particle. So instead of having to control one qubit at a time, you can control the whole set of qubits. Okay, but um, that are in a research mode. Still, it's still in a fundamental research where experimental work is being done. Okay, if we are talking about TRL, it's still in TRL1, TRL2. Same goes to frequency. There are works in frequency spatial domain to perform quantum computer. But I have no in-depth detail on that.
Okay. And
And then the second one?
yeah, continuing from the first question, he said, with deep learning, the second question, what is the simulation to do is quantum? Any specific framework or platform, Cik Hafiz?
Okay. Okay, in 2021, each year IBM Quantum will held a quantum summer school.
Mm.
Okay, and in 2021, the whole summer school was talking about quantum machine learning. So there's a lot of example and there's a lot of application in quantum machine learning, such as quantum gun. There's also quantum gun. There are also quantum classification, such as quantum SVM, where a lot of process in machine learning that can be shortened. For example, if you were to work in deep learning, you need to perform training for your neural network. Those neural network, the workload of identifying what neural network works can be shortened using quantum methods. Okay, then there are also work within quantum realm where you have a lot of qubit setting, and then you want to perform example classification process to ease quantum computer processing, also can be done. It's not that okay. The easiest way is, if you have a machine learning problem where the processing time takes a lot of time, or the optimization takes a lot of time, that is where you can perform quantum computing in that process. And if you are looking at quantum computer, if there's a process of regression or process of classification of workload within the quantum computing framework, that is where machine learning works in quantum computer.
Okay. So hopefully it gives some better idea lah. I think from I believe this is quite new topic for some of you, even myself. I think I have another question. Maybe we limit for another 2 questions. The next question is Hafiz. I think the question is about related to Unimap. When Unimap started its QC research, right? Which areas of QC is the core of them? So this is the questions from I think from SF. Any specific topics by Unimap when they started on QC?
Oh, actually, Unimap is doing research on quantum encryption. So a part of the quantum encryption activity was to identify implementation of quantum computer. So the fastest way to come up with the result is to perform quantum machine learning in their study, which is at the moment it was about understanding the property of a plant. So we examine that. It doesn't relate directly to the funding that they receive, but actually it's just an initial work for quantum information activity in Unimap. I do notice that any research that has performed a quantum network activity previously, high chance those people will do the same, will be the same people that will be doing quantum computing, because they have the knowledge of the settings, they have the knowledge of what are the parameters that they need to control. So it's about to find the budget that they can purchase those equipment lah.
Okay, thanks, Hafiz. Is there any, I think last questions, if there is any one more questions from the participant. If not, I really want to ask as well. Anyway, okay, Hafiz, I think hopefully this is like the last question. Any good first I just want to get more ideas on the community on quantum computing in Malaysia. If you know and you may share with participant, I mean the audience today. And second thing is about the support from the Malaysia government. If you know any government agency that provide these kinds of support to conduct or to support any specific group in the quantum computing in Malaysia. That's my two questions, Hafiz.
Okay. 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 First of all, I was involved in preparing a paperwork to apply grant for quantum computer activity. But we all know, because if you were to execute a hardware quantum computer, that will be hard.
Yeah.
The budget is quite huge. I see. So that's why it's quite hard to uh, to push for quantum computer hardware. But it might be easier if we push for quantum computing software. In Southeast Asia, for all of you, for your information, there's only 4 company related to quantum computer, and those all 4 company are in Singapore. There's no company in Thailand. There's no startup in Vietnam, Brunei, Indonesia. No. As far as the 258 companies that I have observed lah. Okay. So if you were to go to any quantum computer cloud services and try on the tutorials or do some analysis on top of their free qubits, it might not be much, but still okay for a starter.
Okay.
Then you'll be the first people in Malaysia doing it.
I see.
There's not much. I mean, there's not much exposure for quantum machine learning or quantum programmer or quantum developer.
See.
So that's why we don't see much of papers or application or grant apply for quantum computing, because the notion is that those who are pursuing for quantum computer is there's a high probability they are from hardware.
I see.
So that's why the application of grant is based on the hardware specification. And that is why it might be rejected because of the high cost.
Okay, so so that's mean from what you mentioned just now, we are still seeking for the support from any government agency on running this quantum computing kind of activity, research activities lah, is it?
Because my intention of having this kind of presentation is so that for engineers or researchers out there, for a group of people, a silo group of people to apply for a grant, it might be hard. But when you have a community, it will be much more easier. For example, in US and Canada, it started off with small groups of people doing research in silos, and then when they combine, they propose a policy. So that's why there is a written policy for a quantum computing roadmap for both Canada and America. I believe other companies are pursuing also, such as the Netherlands. They are in progress. In US and Canada, it does not start with research.
I see.
The policy goes to even to the schools, to the level of the schools. It's not just university, it's not just polytechnic, it's to the schools.
Okay. Okay, a lot of things to work on. I think I believe you have a small group as well to work on this one. So I believe this is your context, right? For us to communicate and to discuss about quantum computing in Malaysia, I believe.
Mm.
Right. Okay. I think allow me to get to read one final question, Hafiz. I think from Adib before we end. What are the directions of quantum architecture? Will it follow the von Neumann? Hopefully, with something you can respond on this. Yeah.
Mm.
Is there
Quantum
you want to respond? Oh, yeah.
Mm. Okay. It's hard to answer that question because for each and every type of quantum, there are different framework architecture. Um, and my interest is more on quantum computer that is related to photonics, which I understand more compared to semiconductor, for that matter. Such as I might not answer that directly, but in photonics, um, the way of moving forward for quantum computing is um, to minimize the setup from physical optical setups to silicon photonic setups. That's the dream of any photonic quantum computer, because having in those kind of condition, we can reduce the footprint for the numbers of qubits that we can have, and also increase the numbers of qubits within that same footprint. So that I can answer for quantum for photonics, but for other technology, I don't have that much knowledge.
Okay. All right. I believe that's the reason why Encik Hafiz share the link and everything here. Feel free to communicate further. Then I believe the big QR code on the screen will help a lot to all those who are interested on this area, right? I think again, Encik Hafiz, we are running out of time. We reaching 4 o'clock today. Again, I would like to thanks Encik Hafiz for joining us as a speaker to give a lot of informations and discussion on quantum computing related topics. I think allow me to invite all participants, if you are okay to open your camera, and then I think maybe Hafiz can release the screen first, and then we can have group photos. If you are okay to open your screen. Okay, thanks. Can we? Okay, thanks. The others, if you want to open your camera before we take a photo, a group photo. Okay. How you can get the photo? I think later on, we can share on the specific links. Then you can get it your photo. Okay. Right. So 1, 2, 3. All right. Okay. One more. Okay. 1. Hold on. Once again. Okay. 1, 2, 3. Right. Okay. Again, I would like to thanks Encik Hafiz for being our speaker today. I think with that, I end the session for our July talk from IEEE KL subsections and co-organized by CAIRO UTM for this event. Again, Assalamualaikum and have a good day ahead. Thanks, everyone.
Waalaikumsalam.
Thank you, Doctor. Thank you.
Welcome. Okay. Thanks, Hafiz.
Thanks, everyone.